ladies and gentlemen, my name is Yogie Lutfi from 11 Maret University, Indonesia. I want to present our research entitled is ultimate strength value of stiffened panel designed under initial displacement and applied pressure, finite element analysis comparison with IXGSR. This presentation includes introduction, configuration of finite element analysis, and then result and discussion, and the last is conclusion. Number one, introduction. Sea transportation widely used due to its huge trading volume and the low cost of ship transportation. The safety effect of structural assessment of stiffened panel and ship structure under different loading scenario has been studied. However, in report by the European Marine Safety Agency during 2014 until 2020, there were 1,500 accidents on EU flag vessel, and of all these accidents, 58 were caused by hull failure. The purpose of this research is structural evaluation of stiffened panel, subject to transfer and lateral pressure acting on the bottom and side plates. Number two, configuration of the finite element analysis. Hull reference model, as we can see, figure 1, hull grider section, cross-section of hull carrier, point A 3D model, and point B is 2D model ISSC 2000. And then the hull carrier has 30 and 24 stiffened panel. The selection of the model for the study include the stiffener number 2 and 3 according to figure number 1 in this red box. And then geometrical modeling. And the difference between the two models in thickness and flank. Thickness, flank, and height web, as you can see in figure number 2. And then element discretion in this work is set to 25 millimeter in size on the overall geometry like figure 3. And then boundary condition in this modeling can be seen in figure 4. Applied loading scheme, as you can see, figure 5 is panel illustration. Point A, it is a schematic 3D model of an overall panel, and point B, the 3D model in the current finite element analysis with the applied loadings. The applied loading scheme, they are in 2 steps. Step number 1 is pressure 0.16 megapascal as lateral and transversal. And then step number 2, impulse displacement 5 millimeter as axial compression. Number 3, result and discussion. Design panel geometry. After simulation, as you can see in figure 6, step 0.0, the model before applied the load. Then the result for the initial step or 2.0 are obtained in figure number 7. The model only accepts the pressure force without axial compression. The force is obtained from the pressure under the plate and side of the plate. As the result, the middle part of the model has the high stress. After adding axial compression, the stress obtained by the model will be higher at each step. At step 2.8, experience the ultimate strength of the model. The model reached ultimate strength so that the strength of the model is at maximum level. When the simulation increment is continued, the model will distribute its stress until it cannot be endured. Based on the result present in figure 8, it can be concluded that the stress in model focus on the center, which is affected by axial compression. Then there are bends in the model both from the plate, web, and flank. This was influenced by the high stress that the model could not withstand. This phenomenon is called column buckling. After analyzing its increment, the result of the light and heavy model as present in figure 9 and figure 10. Two conditions are given, pressure and without pressure. It is found that there is a slight difference in the ultimate strength between the two conditions, which specifically occurred in the stress range 250 megapascal until 300 megapascal, and strength 0.001 and 0.002. The estimation of this difference is not higher than 5% of overall stress. The structural behavior observed in post-ultimate strength was achieved as closer 0.004. The like model with and without pressure, put the stress was fallen to approximately 190 megapascal. An opposite tendency is recorded from the heavy model in figure 10, in which after the ultimate point was achieved, the stress behavior was found to decline as the strength approached strength 0.004. The stress of both the heavy model with and without pressure was put higher than 200 megapascal. Even though the model without, it can be taken as an initial conclusion that the pressure effect is lesser in the proposed heavy model. Then comparison of the finite element result and Ajax regulation. This is a table comparison. Additional loading has a negative effect on the ultimate strength value, reduce the ultimate strength value. The decreasing ultimate strength value is in line with small inertia of the area of the model. Reduction of the ultimate strength record in the rank 4 until 7% for model without pressure in finite element simulation, and 1.5% for the calculation using IFGSR regulation. Number 4, conclusion. In this research, the ultimate strength calculation was carried out on a design stiffened panel as an idealization of the full carrier structure. The model is divided into two, namely the light model and the heavy model. The choice of the model refers to the location of stiffened panel, the sides and the bottom of the hull. The ultimate strength calculation is carried out based on IXCSR 2022. Under buckling condition, there are two loading, pressure with value of 0.16 megapascal and imposed displacement on both sides of the web of 5 millimeter. The addition of pressure has a negative effect on the ultimate strength, or can reduce the strength of the model. The smaller the inertia of area, the lower the ultimate strength. And then the ultimate strength simulation result saw a decrease from the IXCSR 2020 ultimate strength. Thank you for your attention.